Good day, ladies and gentlemen. This is the first part of the 14th lecture related to the introduction to the RM software for filter design. We will speak here about the bilinear transform of analog transfer functions and response analysis. This is the content of this presentation. After the introduction, we will give a short background knowledge, allowing to enter the subject. Then we will develop transformations which are based on the derivative approximation. Using these transformations, we will transform the functions and then perform transfer function analysis in the new domain, transformed domain, which is named here Z domain. And finally, we will give several words about the program which is performing this business, this action, which is named bilinear transform. It is about the problem of synthesis of filters for discrete signals based on existing solutions of analog filters, which are abundant, and as we will see in the succeeding lectures, may encompass a wide variety of transfer functions. To exploit these solutions, various methods have been used for mapping the analog transfer function, which is the S domain, into a discrete time function, which would be the Z domain. So designing analog SC, switched capacitor, and digital infinite impulse response filters. We may group these methods in two parts, two groups. The first group consists of methods which implement a specific criterion of approximation, such as the impulse response invariant method, the modified impulse response invariant method, the step response invariant method, or the zero-order hold method, the magnitude invariance method, and the phase invariant method. The methods in the second group are based on substitution of the complex frequency in the S domain by a function of Z. In that way, we get the matched Z transform method and a pair of methods obtained by approximation of the analog integrator by a digital one. The last two are known as backward Euler, or backward difference, and the trapezoidal method, or the bilinear transform. Finally, a second-order method was introduced lately. None of the above methods are universally successful, hence such an abundance of ideas emerged. Here, the development begins with a universal expression for the derivative approximation. As a result, the so-called bilinear transform will be developed. It will be in the center of our attention in the rest of this presentation. A discrete time signal, as depicted in the figure on the right, may be represented as a series of value of the voltage and sum of delta functions which are shifted in time. Here, Ts is the discretization time interval. So, sampling of the voltage Vd, of the voltage V, to produce voltage Vd, discrete, is performed every Ts seconds. After implementation of the Laplace transform to this series, a new expression arises in which the complex frequency S is introduced, and the delay between the samples is here expressed as an exponential of SLTS, which brings the idea of introduction of the Z transform, which is expressed in the second expression on the right. After substitution, we can obtain the discretized voltage in the Z domain expressed as a series of amplitudes multiplied by the number bar Z to power minus L. We understand that the last expression represents sum of amplitude pulses mutually shifted by a proper delay of Ts. The value Z to power minus 1 is interpreted as a single delay. Here, before proceed later on, we will shortly study the Z transform. Assuming Ts equals 1, the table depicts the mapping from S to Z domain. So the origin is mapped into unity, real unity, while plus the imaginary half of pi, plus minus, is mapped into imaginary unity, plus minus. The imaginary pi plus minus is mapped, both of them, into minus 1, and 2 pi positive is mapped into unity, and so on. Given a transfer function in the S domain, a question arises as to how to obtain its counterpart in the Z domain. That is important from the point of view of using existing continuous time filter function to create discrete time filter function and consequently discrete time processing system filters. The following general procedure may be implemented for that purpose. First, do approximate the derivative here to do discretize the time and transform the differential equation describing the system into a difference one. Second, apply the Z transform to the resulting difference equation. And third, substitute 1 over s by the approximate expression obtained in the previous step. Now we will go a little bit into details. The transfer function in the S domain is usually expressed as the first rational function above, which in fact has its origin in the time domain, represented as a differential equation, which was later on transformed by the Laplace transform to produce the transfer function. On the right-hand side, a schematic shows graphical interpretation of the differential equation discussed here on the equation 2. So the coefficients are expressed by the triangles, and integrating the derivatives is expressed by integral units. So when we go through the middle, the last coefficient, the a0, is not integrated, but the first coefficients, ak, is integrated k times. So every integrator may be expressed as shown here, the output and the input, and when Laplace transform is taken, it gets the form S multiplying G equal F of S. So to complete the transformation of equation 1 into a discrete transfer function, one needs to transform 3 into the Z domain and substitute the integrators. The rest remains the same. Any derivative appearing in the definition of the transfer function, which was expressed as equation 2, may be expressed using the linear multi-step formula in the following way. Here on the right-hand side, the derivative, time derivative, is equal to the sum of the value of the function in the same instant and set of values are values of the value of the function and the derivative in previous instance. R is referred to as the order of the multi-step formula. By proper choice of the parameters in this formula, one may produce different integration rules or rules for approximation of the derivative. For example, if r equals 1, alpha 0 equals minus 1, alpha 1 equals 1, and beta 0 equals 1 with beta 1 equals 0, one gets the backward Euler formula. Which is expressed as the first signal here, first expression here. So after implementation of the Z transform, it will become the same, but now we have delay 1 minus Z to power minus 1. So we have the function and the delayed function, because there is no derivative since b1 is 0, beta 1 is 0. So now by comparison of the equation 3 earlier and this formula, we come to the analogy that S should be substituted by 1 minus z to power minus 1 divided by t, or the proper transformed expression. This is the backward-Euler transform, which means wherever in the S-domain transfer function we see S, we put this expression to get a Z-domain transfer function, which will be used for switch capacitor and recursive or infinite impulse responsive filter synthesis. Now, the more important thing is the trapezoidal rule, which is the most frequently used in this area, which arises where the order of the formula is 1, alpha 0 is minus 2, alpha 1 is 2, beta 0 is 1, and note beta 1 is 1 now. So the derivative of the previous instant is present also. And after the manipulation, we get on the bottom the so-called bilinear transform. This expression is substituted whenever S arises in the transfer function. So before proceed with the implementation, we will discuss a little bit the properties of the bilinear transform. First, on the left-hand side, there is a formula in which the Z is extracted on the left-hand side and expressed as a capital sigma plus j capital omega. And on the right-hand side, the S is substituted and expressed by lowercase sigma and lowercase omega. So this is a formula which allows the mapping from the S into the Z domain. So we are giving the coordinates of the S in this S domain, points in the S domain, and then we get points in the Z domain on the left-hand side. This is done, and some values are shown here in the table. The first row, the first two rows, are saying what happens with the imaginary 1 and imaginary minus 1. These both map into conjugate complex numbers, which, as we will show later on, lie on a unit circle. The origin from the S domain maps into +1. So again, on the unit circle. +1. So this is a number on the real axis in the S domain. Maps into a real number, but outside of the unit circle. The opposite happens when the real number, the real coordinate from the S domain maps into the Z domain. The resulting number falls inside the unit circle. So if it is on the left-hand side of the left half plane, it will be inside the unit circle. If it is on the right half plane, it will be outside of the unit circle. Then The two last rows are speaking about what happens with the infinite. If a real infinite number is in the S domain, the infinity, it maps it into -1, which is the case if imaginary number is to be mapped into the Z domain. So the infinity maps into -1. This is illustrated here. The infinities are not shown because they cannot be shown as such, but we can see now the numbers. So the imaginary coordinates, which are at 1 and -1, j1 and j -1, are the two red dots on the right hand side, which are on the unit circle outside of the axis. Then the 0, the origin, is at unity, real unity on the circle. The +1 is at 1.5 or positive, and -1 is at 0.6 and so on at positive. Here, at -1 is shown where do map the infinity, which cannot be shown on the left-hand side. So having now the feeling about the properties of the mapping, we will continue now to see the consequences. One may recognize that the imaginary axis of the S-plane is mapped into a unit circle in the Z-plane. Points in the left half of the S-plane are mapped into the inside of the unit circle, while the ones from the right-hand side of the S-plane are mapped outside of the unit circle. The origin of the S-plane maps itself into 1, while the infinity into -1. We will use the opportunity here to discuss shortly the issue of stability and minimum phase. A continuous time filter is stable if the poles of its transfer function fall in the left half of the complex S-plane. That comes from the need for all expressions in the pulse response to have negative signs, all exponents to have negative signs, which will allow the response to decay to 0 at infinite time. A discrete time filter will be stable if all poles of its transfer function fall inside the unit circle in the Z-plane. Having in mind the figure from the previous slide, the bilinear transform maps the left half of the complex S-plane to the interior of the unit circle in the Z-plane, which means that stable filters designed in the S-domain are transformed into filters in the Z-domain that preserve stability. Similarly, a continuous time filter is a minimum phase one if the zeros of its transfer function are in the left half of the S-plane. A discrete time filter is minimum phase if the zeros of its transfer function fall inside the unit circle in the complex Z-plane or are located on the circle. Then, the same mapping property of the bilinear transform provides that continuous time minimum phase filters are transformed into discrete time filters with preserved property of being minimum phase. We will give one example which is related to the seventh order LSMZ low-pass filter with two zeros at the positive imaginary axis. The maximum passband attenuation was set to a max equal 3 dB, while the minimum stopband attenuation was set to a min equals 40 dB. The cutoff frequency of the filter, of the low-pass analog filter, was set to 100 kilohertz. The group delay of this function was corrected with the second order corrector so that the maximum passband group delay error was 1%. The pole zero location of this solution are given in the following slide, where poles are blue dots while zeros are red squares. The transformation was performed with sampling frequency of 1 MHz, that is, it is oversampled. The position of the poles and zeros in the Z-plane are depicted also on the following slide. So let's look on the left-hand side first. So we have blue dots which are representing the poles. First, we are looking to a set of 7 poles which are located in on a line which is almost circular, and that would be the set of poles of the selective part of the filter. It has 2 pairs of zeros at the imaginary axis, and that forms the LSMZ filter. And then we have this quadruplet of poles and zeros, which are symmetrical to the origin, which are representing the corrector. 2 poles on the left-hand side and 2 zeros, which are have equal imaginary parts and real parts with opposite sign. That is the original low-pass filter. And as we can see, we have the mapping on the right-hand side. Everything goes near to the unit circle. So there are the zeros, there are the poles, or they are compressed by the unit circle, and only we have the single zero at infinity, which is the low-pass filter. It has 1 0 at infinity. That is mapped on the -1. The rest are all approximately on the circle. That property may cause numerical problems, since with high order filters, numerical errors in calculation of the elements of the system may be numerical problems, may be enhanced or more because of similarity of the numbers which are processed. We will discuss here now the properties of the transformed function. Particularly, we will look at the group delay. On the left-hand side at this slide, the group delay of both the S-domain and the Z-domain low-pass filter is depicted. That means the x-axis is both analog and digital frequency. One may notice that the curves overlap. And at first glance, one may say that there is no difference, there is no distortion introduced by the bilinear transform. Looking more carefully, however, one may find that there is, in fact, some difference, even though the oversampling is implemented. As you can see here, the sampling frequency is 10 times larger than the cutoff frequency. The discrepancy is seen here at the top peak of the group delay, and it is about 40 nanoseconds, while the value of the delay is about 20 microseconds, which in general may be considered as negligible, but still existing. As is the group delay, the amplitude characteristic is affected, distorted too. The distortion is larger when the value of Fs as compared with the cutoff frequency is smaller. As a specific problem is the fact that the location of the cutoff frequency is now shifted. This shift may be found by the following analysis. What we do here is we have the transfer function of the digital filter, or in the Z domain or discrete time filter, is obtained from the transfer function of the analog filter with substitution of S by the bilinear transform. Now, if instead of Z we search the omega axis where the amplitude and group delay characteristic is calculated, then Z transform becomes the first addend in the quotient here, and so the overall analog function takes the form of tangens of the variable takes the form of tangens of the product of digital frequency and the sampling interval. And as we know, the tangens for small values of the argument is linear, is approximating a linear function, so that there is one can see the tangens as simply as omega with some coefficient. But if Ts is not small enough, that means if the sampling frequency is not high enough, then very soon we will have distortions of the transfer function because of the introduction of the bilinear transform. From this expression, we see that there is a nonlinear relation between the angular frequency in the S domain, omega A, and the angular frequency in the Z domain, omega D. This phenomenon is referred to as frequency warping. We should interpret this result as the gain and phase shift that the discrete time filter has at a frequency omega D is the same gain and phase shift that the continuous time filter has at frequency omega A, which is now calculated by this expression. What are the repercussions of this effect from the designer's point of view? The continuous time filter should be designed to compensate for this frequency warping by setting in advance omega A from equation 5 for the cutoff frequency of the center frequency. In other words, for a given discrete time cutoff frequency, the poles and zeros of the continuous time function are supposed to be divided, renormalized by omega A from 5 before entering the bilinear transform. This is called pre-warping in the filter design. It is the opposite expression for from analog to digital, which is less important for the design point of view. In this table here on the right-hand side, the effects of pre-warping can be seen. Namely, here we are looking for the cutoff frequency of the digital filter, Bessel, sixth order Bessel and Butterworth, obtained by bilinear transformation of their poles with the sampling frequency only 2.5 times larger than the cutoff frequency. Even though the pre-warping was implemented, we may see that the gain at the cutoff frequency at the expected or desired cutoff frequency is different than the desired one. The desired one is 0.707, while for the Bessel it is 0.704, and for the Butterworth 0.691, which generally confirms that oversampling is an important method to preserve the properties of the analog filter when bilinear transform is implemented. Now, having a new variable z, we are producing a new transfer function. So this expression here, HD, is the transfer function, digital transfer function, or discrete transfer function, and it was obtained by substituting the bilinear transform into the analog one. While the expressions look similar, the procedure to obtain this function is not as simple as it looks like. Nevertheless, we have this transfer function, and then for finding the properties of the filter or the properties of the transfer function, we search the frequency domain, which means we put S equals to j omega, and so that the Z variable becomes, as it is written here, as cosinus x plus j sinus x, with x equals omega multiplied by the sampling interval. Now, what is the difference? The difference is that now the variable is not imaginary, but complex. It was imaginary when analog filters were simulated or studied, and now is complex. The second is the maximum values or minimum values of the variables are limited to 1, and the variable is periodical, which means that the response in the frequency domain will also be periodical, of course. Here are expressions for the squared amplitude characteristic and for the group delay, where poles and zeros are represented as complex numbers. Here again, one should repeat that calculation with complex arithmetics is usually avoided in filter analysis, since generally the programs or the compilers does not allow for long double or double arithmetic in complex numbers. So the additional space which would be used for long double variable is in fact used to put real and imaginary parts. So this is why here, and through all these lectures and within the RM software, exclusively ordinary arithmetic, not complex numbers are used. Here is the expression for the phase, which is, of course, normal. It has three components. One is for the argument of the gain at the central frequency. Then we have argument obtained as a sum of arguments of the numerator and denominator. What is important here, again, like we said during the discussion of the analog transfer function analysis, is the fact that one should be very careful in implementing this expression, not to miss the quadrant to which are pointing the vectors as shown here, and so if missing, that means a wrong value for the phase will be obtained. Nevertheless, everything looks okay. In fact, if this attention is not paid, if the calculation is done careless, then a phase characteristic looking as sawtooth will be obtained. As for the time domain, the following expression, which was already used, may be used here. Here x is the excitation. Of course, it is sampled. And y is the response. And this expression says that the response at present time is obtained as a sum of weighted responses of the previous instance and weighted excitations of the previous instance. Of course, the excitation exists at time instant 0, which is not the case for for the response. So the response at the time instance 0 is obtained as a result. It's not known in advance. This expression should be seen as a window. So when the value for one time instant is calculated, all the x's and y's are shifted by 1, so that the response calculated in the previous instant goes to the right-hand side and new one is obtained, and so the calculations proceed. What is interesting here, this is the only situation where we recommend to use the coefficients of the transfer functions, which are a and b here, not the zeros and poles for calculation. This is some opportunistic approach, since the calculation of the coefficients is simpler and more, how to say, transparent, more easy to follow than the alternative, which is a partial fraction expansion and then calculating the responses of every fraction and then adding them and so on, what was done for analog filters. So we came to the program Bilinear transform, which is performing the transformation and analysis of the transfer function. The analysis in both frequency and time domain. This program produces two reports. One is textual report containing all the phases of transformation, including pre-warping, without pre-warping, with pre-warping, and frequency and time domain analysis. Time domain analysis, of course, only for low-pass filters. And another bilinear trans.csv file, which contains only the table of responses and may be used for creation drawings using Microsoft Excel. As an example of implementation of the bilinear transform program, we will here show an 11th order LSM filter with 4 transmission zeros at the positive omega axis, with 3 dB passband attenuation, 60 dB minimal stopband attenuation, central cutoff frequency of 100 kilohertz, and sampling frequency of 1 megahertz. Here is part of the response produced by the bilinear transform program. Of the left-hand side is the attenuation characteristic of the LSMZ filter. On the right-hand side is the gain characteristic of this filter. Then we have the phase characteristic of the left-hand side, and one can notice here the jumps which are attributed to the frequency where the location, which is location of the transmission zero at the omega axis. So there are 4 such zeros and 4 jumps of the vector of the vector phase vector, which changes orientation from downward to upward. On the right-hand side is the group delay characteristic of the LSM filter, which is, of course, monotonic inside the passband. And finally, here is the time domain response to a Dirac pulse, blue line, and to a step function, the red line of this filter. So that would be all for this presentation. Thank you very much for your attention.